Hi guys, today I would like to discuss force between two parallel wires carrying currents in the same direction. Let's try to understand the setup which is given it here. So these two wires are connected to a battery and these two are parallel wires. Suppose if I take this is wire AB and another wire it is CD. So these two wires are, let it be separated by a distance a little r, and these two are connected to a switch, and the switch is connected to cell battery. When switch is on, so through the wires parallel currents flow. It means current direction in the two wires is same. If you remember, a current carrying conductor creates a magnetic field. So we derived from this Ampere's law closed integral B dot dl equal to mu naught I. Suppose if I have one more conducting wire, current carrying conducting wire, and this is also generates magnetic field. So because of these two parallel and both of them current is passing, so they both produce magnetic field. And if one wire is within the magnetic field range of the another wire and vice versa, then the interaction of these two magnetic fields causes force between the wires. That force may be attractive or repulsive, depends on the direction of current. Again, I would like to say, suppose a current carrying conductor creates a magnetic field. So this is the direction of magnetic field. So magnetic force and magnetic field direction always perpendicular when current is flowing. That we can get it from Fleming's left hand rule. Now my point is here, suppose if I bring another current carrying conducting wire within the magnetic field range of the first wire, let it be called AB wire. Now through the another wire CD also current is flowing in the same direction, but this wire is in the presence of the magnetic field of the another wire. Now through the CD wire current is flowing, when current is flowing and it is also magnetic field is there, and that affects the force. Because of that force which is present between the two wires, that is the reason maybe they attract each other or repel each other. When the currents are parallel, then the force between the two wires is attractive. Attractive means in the sense the both forces, they both are coming, the two wires are coming close to each other. When they come close to each other, because one wire creating magnetic field of one pole, maybe north, and another wire is creating magnetic field of another type of pole, maybe south, then only the two gets attract each other. So this is what happens when a parallel currents passes through two parallel wires. It causes the two wires comes close together. So let us try to derive what is the force expression. Before that, let me play it one more time. So when currents are parallel between two conducting wires, then the two conducting wires will attract each other. So that is due to because of the total magnetic force that causes the two conducting wires comes close to each other. Let us try to derive some mathematical expression. To derive the mathematical expression for force between two parallel wires carrying currents in the same direction, just recall first, a current carrying conducting wire creates magnetic field. Or a simple statement, a current carrying wire is a source of magnetic field. Now the direction of magnetic field and current, we can use the right hand thumb rule. So the thumb indicates the direction of current and the curl of fingers indicates the direction of magnetic field. So this is the very basic concept we discussed in this chapter. And how to find the magnitude of the magnetic field? We use the Ampere rule, the closed integral B bar dot dl equal to mu naught I. Now, if you substitute the Amperian loop at here, the magnitude of the magnetic field B equal to mu naught I upon 2 pi r. So we need to consider an Amperian loop of radius r. Suppose this is my Amperian loop of radius r. I would like to find the magnitude of the magnetic field at here. The magnetic field direction is tangential. So this is tangential magnetic field. So the tangential magnetic field magnitude B bar equal to mu naught I upon 2 pi r. So this is the expression for magnitude of magnetic field. And in the previous concept, we discussed one more. So that is, if a current carrying conductor is placed in a magnetic field, external magnetic field. If a current carrying conductor is placed in an external magnetic field. So because of the external magnetic field and current, there is a force comes into picture. So the force will be acts on that current carrying conducting wire. So that force depends upon the direction of current. So that's the reason. So here the force will be acts downward direction when current is passing from, and the force is upward direction when you change the direction of current. So to get the direction of force, we can use Fleming's right hand rule. And we derive the expression for force. Force on a current carrying conductor, F equal to I times L cross B. L bar cross B bar. Or this force F equal to, we can write that in terms of the magnitude of the force or the direction. The cross product of two vectors, it means I times BL sine theta. So the magnitude of the force F equal to IBL sine theta. So these two are the basics to understand the present concept. So one is the magnitude of the magnetic field due to a current carrying conducting wire. So that we will get from the Ampere's law, B equal to mu naught I upon 2 pi r. And the second point is the force on a current carrying conducting wire in the presence of external magnetic field. The force F equal to IBL sine theta. So if you recall these two formulas, then I will go ahead to derive the force between two current carrying conducting wires. Suppose this is the one of the current carrying conducting wire. So let me take this length AB, and I is the amount of current which is a passing. So for a moment I can take this as I suffix 1. Now if I bring one more current carrying conducting wire, so that one more current carrying conducting wire, so if I bring within the close distance. Suppose if I draw this in big size, yeah, this is another current carrying conducting wire. Let me name it as, this name is CD. So this is CD, and through this same current I2 current is flowing. The distance between them is to take as a little r. R is the distance between the two conducting wires. Now let us consider a point. Now if I take a point at here, so I will consider a point at here. So what is the force on CD due to because of the magnetic field of AB? AB is a current carrying conducting wire. So AB magnetic field. So if I take the magnetic field direction tangent at there, so this is the magnetic field due to AB wire, so that I can call B1. Now the CD is in the presence of the magnetic field B1, but through CD current I2 is passing. So at the right point there, magnetic field and current, they both exist. And the current and the magnetic field at there, they both are making at right angle. Okay. Now the force on CD. Force on CD. So if that force, since it is second wire, I can call that F2 equal to, we use the same formula, B I L sine theta, or IBL sine theta. But here more careful, what is the B? Here the B is nothing but B suffix 1, magnetic field due to first wire. What is the amount of current? That is the amount of current which is passing through the second wire, that is I2. And L is the length of the conductor, and theta is angle between B1 and current I. Yeah, B and elemental length L, because I is a scalar, elemental length L. So here the theta value equal to 90 degree, and that 90 degrees we can substitute, and here theta equal to 90 degree. So the force F2 expression will be changes B1 I2 times L. Now how can I get the value of the B1? Magnetic field due to current carrying conductor AB. So if I can draw that separately at here, if current carrying conductor is there, to find the magnitude of the magnetic field at a point, we need to consider an Amperian loop. So let's consider an Amperian loop. So this is the Amperian loop, what we consider. So because of the Amperian loop, if this Amperian loop at a distance of r, so this is at a distance of r, what is the magnitude of magnetic field at here? If I call this is the B1, the current I1 is flowing. So B1 equal to mu naught I1 upon 2 pi r. So here the B1 value will be mu naught I1 upon 2 pi r. Now substitute the two factors at there. Since sine 90 value becomes 1, so I can add it there, that is also sine 90 degree. the force F2 equal to mu naught I1 upon 2 pi r times I2 times L. Sin 90 value goes to 1. Now the force F2 equal to mu naught I1 I2 times L upon 2 pi r. Suppose if I1 equal to I2 equal to I, same amount of currents are passing through them, the force F2 equal to mu naught I1 I2 times mu naught I1 I2 is replaced with as I. Then if we can take that, mu naught I times IL upon 2 pi r. If the currents are same. Now this is the force on second wire. We need force per unit length. So for that we can divide that F2 upon L equal to mu naught I1 I2 upon 2 pi r. So this is the required expression. The force per unit length on the second wire, second wire CD, due to magnetic field of first wire AB at a point equal to F2 equal to mu naught I1 I2 upon R. What about the expression for F1 you can write? Instead of to find the force on CD wire, now I would like to find force on AB wire. So for that, suppose if you redraw the diagram again, just diagram changes. Now suppose if I take this wire as CD, through this wire I2 current is passing. Because of I2 current, at a point at here, magnetic field, the radial magnetic field is there. So let it be the direction of magnetic field along in this direction. So this is the magnetic field which is pointing radially. Now what is the magnitude of magnetic field shall I write? The magnitude of the magnetic field at this point, suppose if I take this is as B2 equal to same Ampere law, mu naught I2 upon 2 pi r. Suppose this is at a distance of r. Now right at here, I am considering another current carrying conducting wire. At the same point, it should be straight. If it is not, just assume it is straight. Yeah, now this let it be a wire of AB. What is the distance between them? Distance between them equal to r. Now there is a force on AB which I called F1 due to magnetic field of CD at a distance r. How we can write that expression? F1 equal to, now this time magnetic field is B2. Now current in this AB, let me take, this is also same direction, this is I1 times L sin theta. Now here same, the elemental length and current direction are, magnetic field direction I and B2 is perpendicular to L, therefore theta equal to 90 degree. So the F1 equal to B2 times IL mu2 times I1 times L. Now plug in the value of B2. So F1 value equal to B2 value equal to mu naught I2 upon 2 pi r times I1 times L. If you rewrite this one, mu naught I1 I2 L upon 2 pi r. So that is the force, the magnitude of the force. Now we need force per unit length. That's very careful. Force per unit length. So that we can call F1 upon L equal to force per unit length, which equal to mu naught I1 I2 upon 2 pi r. So this is the magnitude of the force on first wire AB due to magnetic field of the second wire CD. Now what we calculated, force per unit length F1 upon L and force per unit length F2 upon L, they both are same. They both are same. But what could be the reason that they are attractive? So to find that, we'll apply that Fleming's left hand rule. Since the force acts on the right angle to CD, so in this case, the force, the both forces are acts right angle to the CD. Now they both equal and opposite forces. The force on, I will show, if one force is acting along in this direction, so this I called as F2. At the same time, at the same spot, same direction, one more force, that is called F1. So F1 force which is acting on the another wire. So these two forces, F1 equal to F2, but they both are equal in magnitude and opposite in direction. So that's the reason at here they both are attracting each other. So because of this attraction, the two wires comes close each other. So finally, the force per unit length for two parallel current carrying conducting wires, F2 upon L equal to mu naught I1 I2 upon 2 pi r. Now here we define 1 ampere. It's a very interesting definition. Suppose if I1 equal to I2 equal to 1 amp and the distance between two wires are equal to 1 meter. How the above expression changes? Force per unit length, we represent that small f, little f. So force per unit length F equal to F1 upon L equal to mu naught upon 2 pi times, and everything value becomes 1 and upon 1, which equal to mu naught upon 2 pi. If we substitute its constant and do the calculation, so it gives a number 2 times 10 power minus 7 Newton meter. So this is the force per unit length, not only the force per unit length. So how we define 1 ampere at here? Suppose two conducting wires are separated a distance of 1 meter. Between two wires, a force of amount, force per unit length of amount 2 times 10 power minus 7 if acts between two wires. So this is the amount of the force which acts between the two wires. Then the current which is passing through them, the current which is passing through the wires, we define as 1 amp. Again I am repeating. If two conducting wires are separated by distance 1 meter, the force per unit length which equal to 2 times 10 power minus 7. That is the amount of force, very small force. If that is the magnitude of the force acting between them, then we can say the current through the two wires equal to 1 amp, because here I have taken that I1 equal to I2 equal to 1 ampere. So this is how we define 1 amp, not using any help of potential difference and resistance. Here defining 1 ampere with the help of force per unit length. So this is the final expression for the force acting between two. The force expression, force per unit length, F1 upon L equal to mu naught I1 I2 by 2 pi r. Now let us think like this. Suppose I am having two parallel conducting wires. Now this time one is purple. Suppose if I take this as AB. Now this time current is passing I1 in this direction. Suppose if I take another wire of CD. So this is another wire of CD. Now this time the current in this wire is anti-parallel, I1 and I2, and they both are separated at a distance r. Okay. Now what you could expect? If the currents are same direction, the force is attractive. They both are attracting each other. So this and this, they both attract each other. But when currents are opposite, so the two wires will repel each other. So the force acting between them. So this is the force on F1 and this is the force on F2. The two wires will repel each other. But the expression for magnitude of force, the expression for magnitude of the force per unit length, that expression remains same. Suppose if you can say small f equal to force per unit length, F upon L, or F2 or F upon L, force per unit length, which equal to same expression mu naught I1 I2 upon 2 pi r. So this we are calling as force per unit length. The magnitude of the forces remains same, but in this case only the direction of force is different. That we can apply the same Fleming's left hand rule. Now this time the both currents are acting opposite directions due to the presence of the magnetic field of the one another. Now this time the two forces will act oppositely, then the two wires will repel each other. Let's see that. Same setup, same two parallel wires and connected to a battery via key. Now this time through them two opposite currents are passing. Now you can see the direction of current. When two opposite currents are passing between the two wires, through the two wires, now the magnetic field direction in this case will be exactly opposite to the previous case. So that causes on the two wires there is force. That force will act on each other oppositely. So they both will repel each other. So that's the reason if we change the direction of magnetic field, if we change the direction of magnetic field, so that direction how it can be changed? Here that direction is changed due to because of that by changing the direction of current. So the interaction between the two wires with the one another magnetic fields. Carefully here, the interaction of the currents through the wire with the one another magnetic field, not of its own magnetic field. The interaction of the currents through the wires with the one another magnetic field causes force, and here that force is repulsive force. So that's the reason the two wires will repel each other. But the expression for magnitude of the force, here the magnitude of the force we can write the same, force per unit length F upon L equal to, so mu naught I1 I2 upon 2 pi R. So this is known as force per unit length. Yeah, this is all about which I would like to discuss today's concept as force between two parallel current carrying conducting wires.